Hey, so last couple of lectures, we have been taking a look at neural networks, and our implementation is heard somebody. Okay, our implementation is based on a column of neurons. And so, for example, we could have multi-layer neural network. And one of the things we did is from the training point of view for these networks is as we provided a multidimensional input, we said that because if there are, for example, let's say 100 neurons over here, let's say input is 10-dimensional. So this will come in as 10 set of numbers, which we represent as 10 by 1 vector. So that means all of these 10 lines or 10 numbers will be fed to each one of these neurons, right? So rather than individually taking a look at 10 separate weights, we said, okay, let's represent all of these as one matrix, one weight matrix. So if we call it W1, so we can either make this matrix 10 by 100 or 100 by 10. But in our implementation, we said, okay, let's set up a uniform way of representing the matrix equation. So if we go by the number of outputs, then number of inputs, our math will come out a lot more straightforward, right? So every layer, this is how we decided on the weight matrix. So if there are 50 neurons over here, we said the weight matrix over here, for example, would be which one? What will be the size of this? 50 by 100, right? The last layer, so this is our last layer, that will depend upon how many categories or how many classes we are setting up our network. If it's a recognition problem or a classification problem, then the number of categories is already given to us in advance. For example, if we are doing a digit recognition, 0 through 9, we have 10 categories that we want our network to recognize. So there will be 10 neurons over here. In the very last layer, if we are doing, let's say, 100 different type of images, there's a data set called Cypher10. Oh, sorry, Cypher10 is with 10 classes, Cypher100 is with 100 classes. So then depending upon however many there's an ImageNet data set with 1,000 classes. So depending upon the number of classes, the number of neurons in the last layer will be decided by the number of classes, right? So anyway, if we represent all of these as weight matrices, for example, in this case, W3, if this is 10, as you can see, this will be 10 by 50, right? So then the benefit was, as you are doing in your last assignment, the forward pass becomes very easy. So forward pass, okay. So for example, if we go W1 times X, this is 100 by 10, and this is 10 by 1, right? So these can be multiplied because remember in matrix multiplication, the inner dimensions have to match. So the result will be 100. And you can see because if we have 100 neurons, there will be 100 output. So this part is easy. Then similarly, we can go to the next layer and the next layer. Inside it, we have a activation function and the sum function. So we can put all the details like you guys are doing in your assignment number 3, right? Okay. So then in assignment number 4, if you recall, we discussed a few more concepts. Let me quickly bring the assignment number 4. So let's go over here. Okay, sorry, yeah, both in assignment 3, assignment 4, we were looking at the matrix form of the computations. In assignment 4, the difference was we were looking at the MNIST data set and how can we set it up and do the forward pass and the back propagation, right? So this week I will assign you assignment number 5. So if we go to assignment number 5, so very briefly, what you will see is there are a few other very important concepts. One is learning rate optimization. One of the optimizers, which is very famous, we use a lot, is called ADAM. And dropout, we already discussed last time, where the output of some neurons we randomly will select and make them 0 so that the other neurons learn to compensate for the lack of some of the missing neurons, and the network learns a lot better, right? So one more thing we'll talk about today is batch normalization, which is a very important technique which helps us in stabilizing our networks, right? So as we take a look at learning rate optimization, as neural networks started to become more and more popular, so let me give you a motivation for it, then we'll talk about learning rate optimization. So as neural networks started to become more and more popular and more useful, in the, if we go back, let's say early 2000, there was a lot of interest in how can we make them, make their training more stable, more accurate, as an example. Okay, so from here, one of the very important techniques that we rely on quite a bit is learning rate optimization. The goal over here is, so goal is to learn or train the network, train the neural network as fast as possible, meaning as less of total number of iterations, as fast as possible. Okay, and also achieve best results at the same time, achieve best results. If it's a classification problem, then obviously we are aiming for the highest accuracy, right? So, okay, so what is the idea? See, I gave you a very simple example. For example, let's say we are setting up a neural network. Doesn't matter how many layers we have. From the very last layer, whatever the actual outputs are being produced, we will compare them with the target. In our terminology, A is the actual output, Y is the target or the expected output, right? So then we pass it through a loss function and we get a scalar or one single number called the loss. Then we go backwards. So in the forward pass, we will compute A. As we compare with the target, depending upon our loss function, we'll compute the loss and then go backwards and compute partial L over partial theta. Theta represents, all the parameters, learnable parameters of the network, meaning all weights and biases. Okay, and as we go backwards, if you remember, our update equation was theta equal to theta minus lambda partial L over partial theta. For example, if one of the weights is W5, we will do W5 minus lambda partial L over partial W5. So theta represent any weight or any bias. So this is how we compactly describe the learning process. And this is our gradient descent algorithm. And we talked about last time that rather than taking one individual example, okay, so remember our training data will be given one input, correspondingly one expected output, another input, another expected output, right? So suppose we have 50,000 training data. So we'll have 50,000 of these pairs, okay? Rather than picking just one pair and feeding through the network, computing the loss, going backwards, adjusting the weights, that does not work well in practice. And the reason is, it's like suppose you were in a city, you wanted to go to a certain destination, you ask some person, how do I get there? Somebody will say, go this way. Somebody else will say, no, go this way. Somebody else will say, go this way or go this way, right? So the idea is you ask a few of these, and then even if there's a disagreement, you pick the average of all of these, then most likely you'll get to the destination. So even if one of these training data is not is noisy, is not as accurate, but if we picked a batch, so if the batch size is, let's say, for example, 8, that means randomly we will pick 8 of these training pairs. We will compute partial L over partial theta for example, the entire batch, okay? And then we will divide it by 8. If the batch size is 8, we'll divide by 8 so that once we go over here, we are adjusting the average gradient for each one of these weights and biases. So that intuitively, as you can see, will result in stable training. So when we train a neural network, often, as you guys have already seen, we print the loss during each iteration of training. Okay, and if you pick a very small batch size, let's say you pick a batch size of 1, what you will notice is the loss over here, it might be, for example, 3.81. Then in the next iteration, it may become 4.7. Next iteration, 3.9. Next iteration, 5.2. Okay, so that means if the loss is not gradually decreasing, that means, you are updating, your update amount is too high. So as you will see, if we picked a higher batch size, most of the time, I mean, if it is a proper batch size, you will see it might go up 3.83, but then a few iterations later, it will become 3.75, then 3.62, and so on. So we want the loss, if we plot the loss as a function of iterations, training iterations, okay, we want the loss to keep going down until it stabilizes, okay? Once it stabilizes, meaning it doesn't reduce that much, we should stop the training. Okay, so for example, if we plot the loss, this is here, we should stop training. Okay, we talked about it in the last lecture. What if we continue to train? What will happen? The training loss generally will keep reducing, right? But as we discussed, training loss may continue to decrease, but after a certain amount of training, now it's overfitting the model, meaning it's trying to memorize the training data rather than generalizing it. So if we take a look at validation, if we take a look at the same time validation loss, so what we do is we reserve some of the training data. We call it the validation set. For example, we may pick 5% of the data and use it for validation. So if every iteration, we also compute the loss on the validation set, as we discussed, the validation may also, and then this is how, so if this is our validation loss. Okay, so you will see after a while, the validation loss will start to increase. So that means now we are overtraining the network or overfitting the network. So we should stop, right? Okay, so last lecture, we also talked about because we want our network to do really well on unknown data, not just the training data, right? So so preventing overfitting is a very important goal of creating and training neural networks. So what were the two important techniques we talked about in preventing overfitting? So one was very easy, dropout, and then was weight regularization. Where in the loss function, regularization. Okay, so where, as you saw in the loss function, we may have a normal loss, but then we will add one more term, for example, square of the weights, so that as we take the derivative partial L over partial W, you will see whatever the normal loss is, then this, if I made it 0.5, and I think we used a different, rather than lambda as the learning rate, we may call it beta or gamma or whatever. So then this will become plus whatever our regularization parameter is and W. So meaning, as you can see, if the weights are smaller, the loss will be smaller. So not only will try to reduce this part during the training, but it will also pick smaller weights. And that helps it in better learning and stable training, right? And preventing the overfitting. Okay, so now coming to today's topics. Today's topics are learning rate optimization. Okay, so learning rate, remember we are, in our terminology, we are putting it as lambda. So again, the idea is as we compute the loss, theta equal to theta minus lambda partial L over partial theta, right? So first, let me refresh our memory. Why are we training it using this particular equation? Okay, this equation makes a lot of sense. For example, if the loss is convex, a convex function is, which looks like this, okay? If we assume that is how the loss is, then if this is weight on this, we can pick one weight as an example, and loss, if we put it on the y-axis, right? So our goal is find the weight where the loss is the minimum, because that's the goal of our training. We want the output to be very close to the target output, at which point the loss will become zero or very, very small, right? Okay, so as we discussed, if we start over here, right? So if you take a look at partial L over partial W, which is this partial L over partial theta, you can see the slope over here is positive. Derivative is just the slope, right? Okay, which means if this was the W initial, okay, as you can see from the picture, to reduce the loss, we should be decreasing the weight, right? So you can see our W new should be equal to W initial minus some amount, right? And the amount that we will subtract, meaning how much should we move to the left, okay, obviously will depend on partial L over partial W. So this is positive, okay? And depending upon the slope, we will also then not move it too much, because what will happen if if I pick lambda to be too high, what will happen? What if it is so high, I go back over here, right? So let me see, there's, oh, namaste. So anyway, so this has to be, a very special decrease. So in the learning rate optimization, as you will see, we will control this amount. How much should we go left so that we don't overshoot it? What will happen if we pick it to be very, very less? What will happen if I made it very, very, very less? Okay, then what will happen? We'll just very slightly move it over here, very slightly move it over here, right? So that means how many times we have to go through this loop then? Maybe millions of times. So see, the goal of the learning rate optimization is we don't want to overshoot, but at the same time, we don't want to go to millions or billions of times until we get to the lowest loss. So how can we move very quickly uh, until we get to this target goal, right? So let me, so if the loss function is convex, you might say, oh, just pick, reasonable amount, and we know its slope is positive, so we'll keep decreasing, and even if you slightly overshoot it, you can, go back a few times, and you'll get to the ideal weight, okay? Which is okay for this easy convex case, right? But as we create more complex networks, not just a two-layer neural network, what happens is the loss landscape is not that easy. It's not like just a simple parabola type of landscape. So in more complex networks, okay, the loss may look like yeah, so that's from the chat. That was the question. What if it is with many multiple local minimas? And that's what I'm about to draw. So the loss may look like, right, something like this. Okay. So now you can see what if we started the weights over here? So this is the W initial. Okay. So if we apply, same thing, W equal to W minus lambda partial L over partial W, pretend this is one of the weights, right? Okay. So you can see now the slope is negative, negative, negative becomes positive. So we'll increase this and it may just come over here and say, oh, I'm done. Okay. Whereas from this picture, you can see perhaps the best losses may be over here. This is the best W, which reduces the loss more than anything, right? So, so how do we, train our network so that it does not get stuck into, this is what we call local minima. So a lot of research has gone into how do we avoid the local minima. There's no theory as of now that guarantees that if you do it like this, you are guaranteed to get to the optimal, right? There's a whole field of optimization. I have worked in this area for many, many years. I have a current PhD student where we are looking into coming up with better optimization, including quantum computing, because quantum computing has this concept of superposition where it can examine all the possibilities, no matter what the dimensionality is simultaneously. Uh, Still, we don't have a, we even have tried combining classical techniques with quantum techniques, so we've gotten some better results. But like I said, this is like an unsolved problem. So even in neural networks, so we have some, what do you call, heuristics, meaning if you follow them, most likely you'll come to a close to the optimal solution, but nobody can guarantee the optimal solution, right? One of the interesting things from neural networks point of view is that the landscape has multiple So from neural networks point of view, if we have complex neural networks, like simple ones are easy because they turn out to be a convex function, right? If we have multiple minimas, okay, what I'm trying to say is the landscape usually is like this. Okay, meaning, let's say you came to this minima, okay, and let's pretend this is the global minima. Even though we don't know, but let's assume that is the best that is ever possible, okay? And this is a local minima. So what we have done, what we have determined through experimental, through empirical studies is that the difference between local minima and global minima for neural networks is not that far away. So meaning, even if you get to a local minima, it is good enough. Okay, so you don't have to really look for the global minima. Only thing you have to watch out is, for example, let's say, let me magnify this. Suppose it looks like this. Okay. So suppose your weights are over here. So this is, let's pretend this is the loss. Here's the initial weight, right? So as you see, we have to move the weight towards the left or towards the right, if this is where we were starting. To the right, right? Because you can see the loss will decrease. So what will happen if we pick the learning rate too high? So once again, W minus lambda partial L over partial W. Okay, if we pick, this is our learning rate. If we pick too high, then what may happen is it may jump over here, right? Then because the learning rate is already high, it may go back over here, it may go back over here, go back over here. So meaning it just keeps bouncing back and forth, but it never gets to the actual minima. This will happen especially if this is like a very narrow drop in the loss function. Okay. So, um, so from let's say 2005, when neural networks started to become quite popular, and we were able to see how they could be applied to vision problems and can recognize things a lot better. So 2005 to 2015, these 10-year time span, a lot of learning rate optimization algorithms were introduced. Okay. For example, last time I talked about who introduced dropout. Anybody remembers? The person who got the Nobel Prize this year, right? Hinton introduced dropout. So Hinton also came up with one of the learning rate optimization algorithms. And that's why, he got Nobel Prize, because in the foundation of the learning of the neural networks, he has come up with some beautiful, even though you look back and say, oh, I could have done it. Okay. But, always the person who gets there first gets the credit, right? So, so as I will, if I go to our learning rate optimization, right? So I briefly explain as part of the assignment also what are the popular algorithms, and we'll pick one of them, which is the most popular, called Adam, and we'll program it ourselves so that you know how it works. Okay. So some of the algorithms that are popular are, you'll see over here, and as part of assignment 5, I indicate momentum is one of the popular algorithms. And then if you see, there's one more algorithm called RMS prop. Okay, so if I remember correctly, I may not be, I can verify it later. If I remember correctly, Hinton was the one who came up with RMS prop. Okay, so We still use momentum in many CNN, especially if we are training a CNN and we want to optimize. We use momentum, we use RMS prop. But if we combine both of them, then we come to an algorithm called ADAM, and this is the most popular, right? So as I give you slight detail on, and like I said, there are 20 of these algorithms. Some of them work well in one situation. Some of them don't work well in a given type of loss function. But pretty much majority of the time, ADAM works better, okay? So rather than going through many of these, because ADAM is the best, we'll focus on ADAM and try to understand, you know, what's the idea behind it, okay? Intuitively, the idea is very simple. Okay, let me ask you this. Okay, suppose the loss function is something like, so let me just make it curved like this. Okay, so suppose you are over here. And suppose then it will go back up. Okay. Okay, so my question is, if you are here, so suppose this is our initial W. Okay, should you move a, a lot to the left, given this initial point, or
A lot.
from x-axis point of view, or should you move just a little bit to the left as far as changing the W is concerned? So intuitively, okay, see, think about it. What's the slope over here? Is it small or is it too high? High, right? Because it's more vertical. Okay, so if it's more vertical, so think of it this way, W equal to W minus lambda. Let's fix the lambda to, let's say, 1, so that it doesn't contribute, just for the understanding. Then it is partial L over partial W. Okay, so as you can see, if this value is high, what will happen? You might end up over here, right? So intuitively, you can see that if the slope is high, we want this lambda to be smaller, okay? If the, on the other hand, let's take a look at another example. Suppose the loss landscape is, you know, very gradual. Okay, now if we pick lambda to be small, because the slope now is more flat, so it's smaller. So if we pick lambda to be small, what will happen? We'll just keep moving little bit, little bit, little bit, little bit. It will take forever for us to, you know, maybe after a flat line, it then further drops later on. Okay, so intuitively, if I write it like this, if gradient of parameter, and the parameter is a weight or a bias, is high. Okay, we want learning rate, lambda, to be what? High or low? Low. And vice versa. So what I'm trying to say is learning rate, if we always use a fixed learning rate. So in your current assignments, you have used a fixed learning rate. It doesn't matter what's partial L over partial W. You will pick it to be 0.01 or whatever you decided as you did assignment 1, 2, and 3, right? Even 4. It's fixed. But what I'm saying is fixed learning rate may end up causing problems, you know, depending upon the landscape of the loss function. It may start to run into a situation like this, and it may start to oscillate between these two and never get to the bottom, right? So even in this type of situation, you can see if we are here, what will happen? The loss is high, so we will make the lambda to be very, very small. So you will see because if lambda is high, it may go over here, then it may come back over here, go back over here. So same situation, if lambda is small, then we'll make sure, oh, it's very tiny moving to the left and hopefully eventually get to the bottom. Okay. So intuitively, that's the idea. So the two algorithms that I will describe to you, which we will combine to get to the Adam optimizer. Adam optimizer is one of them will be adjusting the learning rate proportional to partial L over partial theta. It could be W or B or whatever. So this is our momentum algorithm. Okay, one of them, the AMS prop, will be looking at partial L over partial theta square. Okay, so instead of partial L over partial theta, I will be looking at the square of this term to adjust the learning rate. Okay, and if we combine both of these, we will get the Adam algorithm. So intuitively speaking, that is the high-level idea of these algorithms, okay? So they will not be using a fixed learning rate. They will adjust according to the slope of the loss function with respect to whatever parameter we are looking at, okay? So now let me put slight more detail over here. So if we go to, for example, the momentum algorithm, okay? So let me see if you follow it, okay? So there are two equations in the momentum algorithm. When we program it, this is how we'll program it if we wanted to implement it ourselves, okay? And by the way, this is part of the assignment 5, so you can see I explained it there. So let me okay, so let's try to understand this if it makes sense. So beta is our parameter, which I said is typically set to 0.9, okay? And before I explain these two equations, let me also mention, okay, in math, a lot of example, let's say the new value depends on old value. So we are doing some computation where we are repeatedly updating some value based on its current value, right? Meaning there's some recurrence involved. So typically in math, what we have found is if we have some kind of a decaying recurrence, then the to give you an example, an intuitive example, let's take a look at a stock price, right? If you take a look at stock price, it may vary, let's say something like this. For example, this is time, this is price. At some point in time, okay? Suppose this was date, let's pick a date over here, let's say 8/1/2024. Let's say this is 8/15/2024, and so on, right? Okay, suppose we are here and we want to predict what will happen 15 days from now, okay? So, so the idea is, should we just take a look at the previous value and do the prediction, or the one before that also matters, or the one before that also matters, right? Okay, again, depending on the type of problem, for example, 8/1 today is what, 10/19, so you can see it's about 2.5 months ago, right? maybe we'll decide, okay, last 1 month is all we care about. Okay, because what happens more than a month ago does not affect our future prediction. Okay, so in this case, we want the previous information to be decayed. So, what we may pick a decay rate to be, for example, 0.6 as an example. Okay, so meaning our prediction will be 0.6 times, okay, previous data plus 0.6 square times previous -1 data, okay, plus 0.6 cube times previous -2 data, meaning as we go backwards. So our decay rate is 0.6, and we keep taking the square and the cube of it, right? So take a look over here. The previous data, what are we multiplying it? By 0.6, okay? And how about the previous to previous data? So that's what I meant by previous -1. 0.6 square is what? 0.36, right? Then further 0.6 cube will become 0.2. So as you can see, as we keep going more and more backwards, we'll keep raising it to the power. So the effect of that, something that was way back over here, is minimal. So this way we don't have to say, okay, stop after previous 3 times or previous 4 times. We'll just pick the decay rate to be such that it reduces the effect of the past history quite a bit less. So in reinforcement learning, this is a very common technique we use. For example, what if our decay rate is 0.9? So what does that imply? Are we using a lot of history or less history as compared to decay rate of 0.6? So higher the decay rate, we're relying more and more on the historical data, right? More history will be involved. So now let's take a look over here. Okay, so think of this beta as like a decay rate. Okay, so MT -1 is the previous value of the learning rate. Okay, so what are we multiplying? If we pick this to be 0.9, that means in the next iteration, this will become 0.9 times less compared to the previous iteration. Okay, and then 1 minus beta, partial L over so this is our slope, right? So let's pick an example. How pick MT -1. So let's say we are starting out. We randomly initialize the weights. So what will be the value of MT -1 in the very beginning? Okay, let's set it to 0. So in the beginning, MT -1, because this is M of, so T at T equal to 0, right? At T equal to 0, so what I'm saying is, okay, MT equal to beta MT -1. So if T is 0, what I'm saying is M of 0 will become beta of M -1. So M of -1, like M of subscript -1. So I'm saying let's initialize M of -1 to 0. So what happens to this term? 0, right? Okay, so now let's go to, so this is 0, right? Beta is 0.9. So what are we doing over here? This whole thing will become 0.1. So 0.1 times whatever the loss gradient of the loss with respect to a particular weight is. This is the weight, right? And let's pretend alpha is 0.1. Okay, so then how are we updating the weight? The new weight will become old weight minus, this is 0.1, this is 0.1, right? But if you take a look, MT is, see, if I substitute MT, so let me write it over here. If this is 0 in the beginning, right? Then this, as we discussed, MT is what? This is 0.1 times partial L over partial W. Okay, so now substitute this with 0.1 partial L over partial W. So what does our equation become? It becomes WT plus 1 equal to the old weight minus alpha is 0.1, but there's already 0.1 being multiplied. So we are assuming, let's pick alpha to be 0.1. So you can see will become 0.01 times partial L over partial W, right? And this is what we are calling our learning rate, whatever gets multiplied with the part. So this is our. So very first time, what is the learning rate? 0.01. Okay, now let's go to the second iteration. Okay, remember we train in a loop. Okay, so second time we compute the loss again. Okay, now let's take a look what will happen to MT. So MT, so MT previously was 0.1 times partial L over partial W. Let's pick partial L the very first time. Let's pick partial L over partial. Let's pretend it's 0.2. Okay, so 0.2 times 0.1 will become 0.02. You guys agree? Like this MT that we computed very first time. This part is 0. This is 0.1. Suppose partial L over partial W is 0.2. So then MT very first time will become 0.02. Now I'm talking about, let's go to the second iteration. In the second iteration, what will MT be? MT equal to beta. Beta is 0.9 times MT minus 1, 0.02, plus 1 minus beta, which is 0.1. Okay, and partial L over, let me pretend next time when we give it another input, partial L over partial W is 0.3. So this is our partial L over partial W, right? So what will happen to MT? If just to get an idea of the numbers, how is it going to update? So 0.9 0.02 will become what? 0.18, am I right? Okay, plus 0.03 will become 0.21, agreed? Okay, now let's take a look at the second update. In the second update, what is WT plus 1? The old value of the weight minus alpha. Alpha we assumed is 0.1. Okay, times MT. MT is, okay, let me see what would be the, yeah, it's, sorry, MT is 0.21. Okay, but out of this 0.21, let me see what I was trying to show you. This is the old. So let me put the whole value as 0.21 plus 0.1 times partial L over partial W. So suppose I leave it like this, okay? So let me see if I can clarify this. Okay, so if you focus in this one, right? Remember this 0.1 got multiplied by this 0.1. Where's this 0.1 coming from? Where did I get? Oh, that was the alpha. There was 1 minus, so yeah, 1 minus beta was this one. Okay, that came from there. And 0.1 partial L over. So this is same as before, but we are subtracting, we are subtracting so if what I'm trying to say is if the learning rate was fixed, right? Remember this very first time this became the effective learning rate as we multiplied the 1 minus beta with alpha. The learning rate effectively became 0.01. Second time when we go through it, right? I should have picked a slightly different numbers so you could have seen. So as we multiply 0.1 with 0.1, this part still becomes 0.01 partial L over partial W, but there's an additional term 0.021, which is also being subtracted from the previous weight. Okay. So that has the net effect of, again, adjusting the learning rate depending upon the slope over here. So overall, what I'm trying to say is the net result is the learning rate keeps getting slightly updated. There's a past history involved. Okay, this beta is basically looking at previous time. What was the contribution of the partial L over partial W? And based on that, it will have a net effect on adjusting this so that learning rate base, if the slope is too high, it will reduce the effective learning rate. If the slope is too low, I'll try to pick up some numbers so that I can show you based on the slope. So the numbers I picked were not as good from explanation point of view, but if you go home and try this out, right? So whatever this number comes out to be, okay, so in the momentum algorithm, what I'm trying to say is this number will come out to be low, meaning small. This number will come out to be small if partial L over partial W is high. Okay, and this will come out to be high, relatively high, if partial L over partial W is low. Okay, so I'll try to cook up a scenario so that I can show you. And like I said, intuitively, the idea is like this. If you're here, you want to effectively change this W to a small amount. Okay. And so if this is high, we want this to be small. Okay. And similarly, if we are coming over here, then we want it to be changing more so that we can we can get to the bottom relatively quickly. So that is the idea behind these two equations. And that is called the momentum algorithm. Okay. Another way to understand would be if you are, let's say, you have a ball, right? And you're rolling down a hill, down a slope. Is the momentum high if the slope is high, right? So we want to slow down this ball. Otherwise, it will keep rolling and keep going to the other side. So that's why they called it momentum. On the other hand, if the momentum is you're relatively close to flat, you want to move more. So that is the idea behind this learning rate optimization, and they called it momentum. Okay. Okay. Then Hinton came up with this RMS prop. So again, they did some studies and saw in some cases this works okay. In some cases, it does not work as well. So if you take a look, and if you compare the two equations, right, you will see here we called it MT plus equal to beta MT minus 1. Okay. And just focus on, forget what we call it. They called it VT, short for velocity. Okay. Beta VT minus 1. So isn't it same as this one? Right? 1 minus beta, you can see it's the same as this 1 minus beta. So what's the difference? Square of the gradient. Okay. And similarly over here, they added a little bit of an extra term over here because they saw that still, the previous algorithm may not work well in a very high momentum situations. So this dampens it a little bit more. And so that is the idea with this RMS prop algorithm, right? Shortly after Hinton proposed this, another very famous paper came called Adam. I think I have, let me see, did I give you the, yeah. So this is the famous paper. Derek Kingma is another very famous deep learning expert. A method for stochastic optimization event. And that is the Adam algorithm, right? So if we take a look at the Adam algorithm, it's a combination of the two algorithms, okay? And you can sort of see over here, where's this equation coming from? So this is the entire Adam algorithm. So the first one you can see is coming from the momentum. You guys agree? This equation, right? Where's the second equation coming from? RMS prop, right? And then they added a few adjustments over here. So we basically, every iteration, we apply these 4 equations to come up with the effective learning rate. This VT, as you can see, already contains the partial over partial WT square, right? And so this contains the information over partial W square. Okay. If you take a look at MT hat, this depends on MT. And if you go to MT over here, the first equation, you'll see it contains the partial L over partial W information. Okay. So you can see it is looking at both the first derivative and the square of the derivative to have a better handle on how fast we should move so that we don't overshoot, because overshooting is, so once again, the goal is we want to move as quickly as possible without overshooting it. So that's where these equations basically constrain it so that it will move quickly, but stabilize at its gets as the partial L over partial W starts to decrease, we also decrease so that we don't overshoot too much, right? Okay, what are the initial values of MT minus 1? Can you guys guess 0 if we program it? See, beta 1, beta 2 are the parameters. And alpha is the parameter. Okay, this epsilon is just so that the denominator does not become 0 and we make it infinity. So epsilon is like typically 10 raised power minus 6, for example. Okay, these are fixed. For example, typical values of beta 1, as I mentioned at the bottom, beta 1 is typically 0.9, beta 2 is 0.99. Okay. So beta 2 is controlling the amount of the square of the gradient, and beta 1 is controlling just the first, I mean, without the square, just the gradient with respect to the weight, right? So these are fixed. These are fixed. Okay. These 4 equations we will perform during our loop as that we are writing in our training loop. And this is how we will adjust the weights, right? Okay, so my question to you was, if we are programming it, right, as we write this equation. So let's focus on the first equation. Partial L over partial WT, you already know how to compute it. You've been computing in all the 4 assignments. So this is, you will compute based on the loss function. Do you know this term? That's already fixed, right? As we saw, beta 1 is 0.9, beta 2 is 0.99. So you'll fix it to 0.9, you'll fix it to 0.99. So this is known. I mean, we can compute it because it's fixed, right? Beta 1, 0.9. So what about MT minus 1? What will be the value in the very, very beginning? 0. So you'll start with 0. And first time you will end up computing MT. Then next time in the training loop, this MT minus 1 will become the old MT. So this is pretty straightforward. Okay, let's go to the second equation. Is there any difference in the second equation? What is VT minus 1? 0. Okay, so can we compute VT then? Easy. Okay, now let's go to third equation. Okay, do we know MT from the first equation? Yes. Beta 1 is fixed. What is T? Very first time T will be 0. Anything raised power 0 is 1. Second time it will become T raised, beta 1 raised power 1, then beta 1 raised power 2, and so on, right? So this MT hat can be computed. Okay, like I said, T will keep changing 0, 1, 2 as we go in the training loop. Okay, this is the iteration in the training. What about VT hat? Same thing, right? Can this be computed? Yes. Now let's go to the weight update. WT, this is the old initial weight, which was randomly initialized, minus MT hat. Do we know this term? Alpha is again fixed in the beginning, for example, 0.1. Okay. Divided by VT hat, which we will know from the third equation, plus epsilon, which is a small number. We write so that denominator does not become 0, just in case VT becomes 0. Okay. So this is how we'll update. And in assignment number 5, I show you exactly how you'll program it. So let me see if I can quickly show you. Okay, so in the layer class, so if you take a look here, it's our layer class. right? Let me make it even bigger. Okay, in the layer class, in the init function where we do the initialization, I have a section on for, right? So MTW, MTB, VTW, VTB. Okay. So what is MTW? Oops. Okay, so MTW is this MT, VTW is this VT, right? And oops, where did it go? Okay, so you can see one for the weights and one for the biases. Okay, so two of them, NP.zeros, means we are initializing the MT and VT to zeros. So this is basically, like I said, in the equation, MT minus 1 and VT minus 1, both are initialized to zeros, right? Then as we go into the training loop, okay, so in the training loop, we will compute the gradients. Then we'll call this function update gradients and biases. And you'll see if we are using the Adam optimization, okay, so we have to compute the G, what were these equations? Okay, what page I'm in? I'm page 8. So if I go to, so now you'll see we have to compute these 4 equations, okay? And so in the comments, as you will see, let me go to page 8. Yeah, page 8, okay. So anyway, if you, for example, take a look at, so these are, okay, so these are just the variables I am declaring. So what are the weight gradients and the bias gradients? I just call them 2 variables, right? So you can see here are the equations that are being implemented. Remember, the first equation was the old value of MT. This was MT minus 1 plus 1 minus beta, the partial L over partial W. So this GTW over here is partial L over partial W. And this GTB is basically partial L over partial B. Right? And like I said, this is the first equation, this is the second equation, this is the third equation, and sorry, first equation. Okay, because this is the first equation for the weights. This is the first equation for the biases. Then this is the second equation for the weights where we were computing VTs, right? And so on. So you'll see the same 4 equations are being implemented. And when you do this assignment, okay, I wrote it so that we can see the effect of it, meaning if we don't put any learning rate optimization, which means it doesn't mean where it's not learning. It means the learning rate stays the same in every iteration. It's constant, okay? And if you compute the accuracy and how long it takes to get to that accuracy, you'll see perhaps you'll get to a similar accuracy, but it will take you quite a bit longer to get there, right? With Adam, it will get there in less iterations. And in some cases, the accuracy may be slightly better because, like I said, it will not overshoot. It will come to the minima for each weight, okay? And because the gradient of the weight, let's say we have 4 weights in our network, partial L over partial W1, partial L over partial W2, W3, and W4. So my question to you is, see if you follow it. Okay, will it use the same if we are using Adam? Will it use effectively the same learning rate for all the 4 weights in every iteration, or different? Different, right? Because the loss with respect to the weight will be different. So, so intuitively, you can think of it this way. One of the weights may be changing faster, another weight may be changing slower. So if this is currently this is where we are for W1, this is where we are for W2, right? Each slope will be different. So what will Adam do in this scenario? Will it adjust W1 quite a bit more or less? What's the slope over here? High, so it will adjust it less. What about W2? It will adjust it more because the slope is less, so it can go farther, right? So that's what Adam is doing, and that's why Adam is very popular, because individually, based on the weight, how the gradient is changing for individual weight, it will adjust the learning rate so that we quickly get to as less of a loss as possible, right? Okay, so now that you have an idea of coming back to assignment number 5. Okay, what I will also recommend is lightly read this original paper, okay, so that you have a better idea of, what was the motivation of the authors. And like I said, intuitively, it is not too difficult to understand, because what they did is they combined the 2 techniques once again. One is a simple momentum, which simply says if the slope is high, reduce the learning rate. If the slope is more flat, increase the learning rate, right? However, then they found out in more drastic cases, it still will not work as well. And this is where Hinton said, okay, let's take a look at the square of the slope, not just the slope. And then these guys said, no, let's combine both of them, because in some cases, even the square is too pessimistic. So we can be a little more aggressive, and let's come. So at a very high level, that's the idea. Okay, but Adam is pretty much everybody uses Adam these days, right? Okay, so I'll give you a short break. Then next topic I'll cover dropout, you guys already know. So even though you will be still playing with it in this assignment. Okay, batch normalization is another very powerful concept that we use. For example, all large models these days use some variation of this batch normalization. So what exactly that is, we'll talk about it. So I'll give you a quick break to recharge. Yes, MT -1 is the previous, and each time we go into the MT equation, we use the old value of MT. And MT is the same as the one we got from momentum, yes. Okay, so next topic I'll explain to you guys is another important concept in training deep networks, and there's a technique called batch normalization that we often use. Let me give you the idea of normalization first, and then we'll take a look at batch normalization. So let's say we are given some data as an example. And we can take a look at, for example, two-dimensional data, right? So it doesn't matter which application it is. Let's say the data looks like this. Okay. So in data analytics, in learning from data, which is basically what neural networks do, is, they given some known data, we try to create networks so that they can do a better prediction, better recognition, and so on, right? So it's a proven concept in statistics that if the data is not centered around the origin, because in extreme cases, the data may have some very high values or low values, right? One of the things we do is we try to move the data. So if this is the data, we'll try to move it somewhere around the center, okay? So how do we move the data so that the mean of the data is centered around the origin? Very easy. We basically compute the mean and subtract each data item from the mean. So for example, let's say this is somewhere, roughly speaking, x of 100, y of 80, right? And let's pretend somewhere over here, the middle point has an x of, let's pretend 60 and y of 50, right? So every data point, we will subtract minus x of 60, y of 50 as an example, right? So the net effect will be all of these data points will end up moving around the origin, okay? So this way, whatever the shift was, regardless in x or y, when we subtract from the mean, we take away that effect so that we can now see relatively how one data is related to another. Similarly, sometimes what happens is data may be far apart from each other, okay? So we try to also bring the data together so that we can, again, focus more on the relative relationship of data rather than how far or how shifted it is. So typical technique is to divide by the standard deviation. So this is our standard approach in normalizing the data. So this is what we call data normalization. Okay, so what happens in neural networks is, so for example, if we are trying to train here some neurons, some weights, and others set of neurons, right? So as we discussed, our data comes in during training, and we don't pass it one data item one at a time, right? As we discussed, we pass a batch of data. Okay, and it's a high dimensional data, which means, for example, if the batch size is, let's say, 16, if this is the batch size, and let's say the input, let's pick the MNIST example. Remember in MNIST example, we had 28 by 28 images. So as we linearize them, convert these pixels into a column of vectors, remember what was the size? 784 by 1. So now you can think of it, the input data during training is going in as 16 by 784. If there are 100 neurons over here, then what will be the size of data that comes out of over here? Okay, see, think of this as 16 sets of data. Each set is 784. Okay, remember if we feed in 784 through 100 neurons, what will it do? produce 100 outputs. If we send 16 sets of these 784, this will be 16 by 100. Similarly, suppose the next layer is 10, you can see the output will become 16 by 10. So, so the batch size stays constant because, you know, that, like I said, think of it as if we were passing one at a time, but there are 16 of these that we are passing. So again, as we accumulate those, it will still be 16, okay? Only difference is during training, we will take the average of the gradients of these 16 and then do the backprop, right? Okay. So coming to batch normalization. Okay, remember the general meaning in statistics and normalization is what? Subtract the mean divided by the standard deviation, right? Okay. So what about batch normalization? What will we be doing? Okay. So here, as you can see, you know, and again, when we talk about the mean or we talk about the standard deviation, the question is, what mean are we talking about? Are we talking, so for example, let's go to the this part over here, okay? What mean are we talking about? Are we talking about mean on the 100 outputs that it's producing? Or are we talking about mean along these 16? See, if I put it as a matrix, right? How many rows and columns will there be? There will be 16 rows and there will be 100 columns. So there are 100 numbers and there are 16 rows over here. So again, from mean point of view, are we taking the mean across here, these 100, or are we taking a mean across the entire 1600? What are we doing? Okay. The mean across entire 1600 will not be meaningful because, you know, they are different data items. So as you can see, we'll do the mean across mean across, mean across these, it should be mean across these, okay? Mean across the 16 because, again, focus on the word batch, okay? Batch size is 16, so you'll be taking a mean across these 16, whatever the average is. Then you'll be taking this second 16, whatever the average is, right? So if we take a look at mean, mean at this point, my question is, what will be the size of the mean vector? How many numbers will the mean produce? Like I said, 16 for 16, we produce one number. And there are 100 of these. So you can see mean will also come out to be 100 by 1. So mean will be 101. And how much is each X of I? Like forget the batch size, individual input data. At this point, it is still 100 by 1. Remember, there are 16 sets of these. So you can see from each 16 sets of these, we'll be subtracting the mean. So that's what, and similarly, the standard deviation will be computed on these 16 data that we are sending for each dimension, okay? So anyway, why do we do that? Once again, this stabilizes the training. Otherwise, like I said, if the data is too far away, shifted in away from the center, or as we divide by the standard deviation, the idea is if the standard deviation is very high in the two-dimensional case, if we divide by the standard deviation, what will be the net effect? It will bring them closer to each other. On the other hand, what if the data is too close to each other and standard deviation is, let's say, 0.3? It's less than 1. If we divide it by it, what will be the net effect? It will move them slightly away from each other. So we want it to be just right, not too close to each other, not too far from each other, and also centered around the origin. Okay, so that is the effect of the normalization. Okay, now you guys, when you guys did the first assignment, right? First assignment, remember the goal was to have the network learn some equation. I forgot, 2x plus 0.3 or something like this, right? So if our, if I draw this, right? What is this 0.3 over here? That's the y-intercept, correct? Okay, so meaning in our recognition between two of these categories, you can see the decision line is not at the origin. It is shifted a little bit above, right? So even though as we are feeding in the data, we are adjusting it, sometimes we need to, as we proceed, we also need to add a bias to it so that it can adjust the decision boundary accordingly. Okay. So to summarize all of these, let me take you to one handout that I have. Okay, so if we go to the 2024 lectures, okay, one of the handout I just added is called batch norm derivation. Okay, so if I show you what is the idea in batch norm. Okay, so this part is one neuron over here. So this part that I draw, this oval shape over here, is basically a neuron. Okay, so what we will do is rather than, so in statistics, when we apply the normalization, if the input data is known, the training data is always given to us, right? So you'll see the mean will be fixed, standard deviation will be fixed. One time you adjust the data and you use it, right? But here, what we want to do is we want to make it learnable, because as it learns, for example, the decision boundary, like I said, it may have to adjust the, move the data a little bit up or down, or even scale the data. So there will be two learnable parameters in our batch normalization. So let me put it over here, learnable. Parameters, meaning during training, it will figure those out itself. One of them is called gamma, and one of them is called beta. So these are the learnable parameters in batch normalization. Okay, so let's take a look at the architecture of a neuron. If we are implementing batch normalization, how does the structure of a neuron change? Okay, so let me see if you can recognize this. What's this over here? Right, so this is the same old neuron, which is doing the sum by taking a look at each input number, multiplying it by the weight, and then summing it up, right? And this is our regular bias. So nothing new over here, same neuron. Okay, suppose we call this S of I. I is the ith neuron in the layer, okay? And then, as you can see, as we move forward, I have one more box over here, which will basically now do the calculation of the mu and the standard deviation. Okay. And the output of this, I called it SI hat. So what is SI hat? Okay. Will SI be a number or a vector? This is one neuron. It's just one number, right? Okay. Okay. However, as I mentioned, during training, will this be coming as just one set or a batch of data? So this will be a batch of data. See, I just showed you one, but pretend here's another. So if batch size is 16, we'll be passing 16 of these numbers, right? So SI, think of this also for the first one, it will be one number. Then second one, the second set of data will be one more number. So if the batch size is 16, how many numbers will be produced over here? 16. Can we take the mean of those? Add them, divide by 16, and that will be the mean. So SI minus the mean divided by the sigma square B is the standard deviation of the or the variance of the data. We take the square root as the standard deviation, right? So anyway, so this, as you can see, all it's doing is subtracting the mean of these 16 numbers, if the batch size is 16 inside each neuron, and dividing by the standard deviation so that all 16 numbers move close to the origin. If they are too close to each other, they will be moved a little bit farther away. If they are too far away, they'll be brought together. So this is standard normalization that we are doing for that we know from our statistics background that helps us stabilize the data, okay? So as you can see at this point, if we examine this SI hat, you guys agree, where will, if we examine, suppose it's two-dimensional data, I cannot draw more than 2 dimensions, then if I take a look at SI hat, in 2 dimensions, where will that be? It will be centered around the origin, right? Those 16 numbers will be centered around the origin, okay? And why? Because we subtracted the mean of the batch. And will they be too close to each other? No, because we are dividing by the standard deviation, so which will make sure they are not too close, not too far away, right? And let's go back to, okay, why do we have this epsilon over here? Yeah, what if the standard deviation becomes 0? Then it will become infinity, right? So this we will typically put to be something 10 to the minus 6, so that it's always some number over here, okay? So anyway, now let's, so we added this extra part, which is computing the mean and the dividing by the standard deviation, right? Then we added one more component over here. I called it BN, short for batch norm. And if you take a look at batch norm, it will take 2 things over here, gamma and beta, okay, which will further be operating on this SI hat and producing some SB, okay? So if you take a look at what is the equation for SB, now take a look at this part. Okay, what is it doing? To each one of these, it is multiplying it by gamma. Okay, let's pretend gamma is 0.8. And then adding beta, beta could be 0.3. So you can see now it is, see, this is basically moving it away from the center. Okay. And this is doing the scaling meaning it will move them slightly further apart or closer, depending upon how the learning is going to proceed. Okay. So anyway, what's the formula for mean? Everybody knows that's how we compute the mean. We add all the numbers. So what will be capital N over here in this example? Is the batch size. Okay, because remember, we are doing it across the batch. Okay. As you can see, what will happen if we pick batch size to be 2 is, as opposed to a batch size of 16, which one will work a little bit better? What's your intuitive thinking about it? Is it better to have a bigger batch size or better to have a smaller batch size? Okay, suppose I gave you 10,000 items in training. Okay, you randomly select 2 of these and you take the average. Okay, as opposed to you randomly select 16 and take the average. Every time you pick 2, take the average. You pick another 2, take the average. You take another 2, take the average. How is this average going to change every time you pick 2 different items? Will it vary a lot? Compare it to every time you pick 16 and you take the average. If you compare these averages to just picking 2 at a time, which one will vary more? Okay. Suppose we're we have 100 people. They vary their age between 0 to, let's say, 80. Okay. I picked 2 random persons over here. Maybe one will be 20, maybe one will be, let's say, 45. What's the average? Okay, whatever, 31, 32.5, right? Okay. Now suppose instead of just picking 2 numbers, I pick 16 numbers, 20, 22, 25, 35, 41, right? So now what is most likely the average coming out to be if I pick 16 persons? What's the rough guess? Give me a number. If we have equal distribution, 0 through 80, so won't it come out somewhere in the middle, right? So what I'm saying is higher batch size will give you more stable averages, as opposed to picking a very small batch and doing the average and doing the standard deviation, right? So as we go along, you will see, for example, if you are picking a data set later on, which is very similar to MNIST. MNIST is too easy. It's easy to get 99% accuracy, but let's go to a slightly more difficult data set, Cypher10. If you are using a batch size of 4 and try to come up with the accuracy, you'll see you will be lucky if you got 70% accuracy, okay? If you pick batch size 16, this will improve. Maybe you'll get 70%. If you pick batch size 32, it will further improve, okay? What will happen if we pick batch size to be 50,000? There are 50,000 images over here, okay? Then the problem is it will take forever for it to learn, okay? So too high of a batch size is also not good, but typically, like I said, you know, anywhere from 16 to 64 for images works out pretty well. Okay. Of course, given the data set, this number may need to be adjusted. Sometimes you'll see people using 128 batch size, right? Anyway, coming back to the architecture has 4 equations. or two extra layers being added. Once you saw a layer that subtracts the mean and inside each neuron and divides by the standard deviation. And the second one does a scaling and moving away from the center. Okay, so even though here we removed moved it, everything around the center, here, as you can see, as we add beta, just like in the equation, as I mentioned, if I have an equation y equal to mx plus c, the c is our y-intercept, so it's moving the whole curve up or down, depending upon what c is. So beta will move it up or down, gamma will do the scaling, okay? Parameters to learn, these are learnable parameters because based on the data, rather than us telling it, hey, use a beta of 0.2 or gamma of 0.7, it will, as we train it, it will learn, what is the ideal scaling after normalizing it and what is the ideal adjustment. So anyway, let's move on. So other than these two layers, what about this F over here? Isn't that the same old activation function? Okay, which could be sigmoid or ReLU or whatever, right? And the output from a neuron, what do we call it? The actual output. And what is Y of I? Expected or the target output. And then let's pretend this is the last neuron. Then it will be the loss, right? Okay, so the question is, from training point of view, as we add these two layers, how will the deltas be computed? Okay, now you can see previously, okay. So the complication is if you take a look at previous neuron, this was our model, right? And what was the definition of the delta if somewhere here is our loss? Delta was, if I call it, let's say S2 as an example, then what was delta? Delta was partial L over partial, meaning the derivative up to this point, right? Okay, now, as you can see, if I go back to the picture, this is our normal delta, which is just before the activation function, okay? Now, because remember, we want to compute the derivative of loss with respect to a weight or the bias, because in our learning, that's what we want to do. We want to do W equal to W minus learning rate partial L over partial W. So if I'm interested in computing partial L over partial W, if I know the delta just up to this point, I still have a few more blocks to go before I can know what's the derivative. So if I can add one more delta, and suppose that is the derivative from here to here. Oops, I went too far. Okay. From loss to here, partial L up to this point, meaning partial L over partial S of I. If I call it delta Bn, if somehow I can compute it, then it's easy. For example, let me see if you understand. What will be, let me put it over here. What will be partial L in this example of partial W2? Suppose I already know delta Bn. Can you give me the equation for partial L over partial W2 in terms of delta Bn? Anybody can give me the answer. Times x2, right? Because remember, which input is connecting to the neuron? if I know the derivative up to this point, what's the equation for SI? Isn't SI equal to x1 times W1 plus x2 times W2? So if I do partial SI over partial W2, only x2 will be left, okay? So it will be x2 times delta Bn. So that's the motivation. Delta, we already know how to compute from your all the 3-4 assignments that you have done. The new thing is, how do we compute delta Bn? If somehow we can figure that out, then we can do the backprop, even when batch normalization is involved, and get the results. So I show each and every detail over here. And let me see. So take a look at, is there a way if I refresh, I can get these? Oh, yeah. So now, because I had too much writing over there. Okay. So let's take a look. Let's go to SI hat. All we are doing is subtracting the mean of the batch, dividing by the standard deviation. Good. SB, scaling and shifting, right? So this equation is straightforward. Because remember, anytime we do the backprop, we have to know how do we go forward. So we have to know how we go forward. So these are the forward equations. Then we will go backwards and compute the derivatives. Okay, mu b is the standard that's a standard formula. Add all the numbers, divide by n. So batch size is 16. We'll add 16 numbers, divide by 16. Correct? This is good. This is the definition of the standard deviation. Subtract the mean from each item, square it, divide by n. Okay. So this will give us the variance as an example, and square root of variance is the standard deviation. Okay. So all four forward equations are straightforward. Okay. So let me see if what will be the delta in this example. Okay, suppose the loss is 0.5 y of I minus AI squared. Let's pretend mean square loss. Okay, so my question is, how will you compute delta? By definition, what is this? Partial L over partial SB. If I further expand it, how would you say it? Isn't it from here to here? And from here to here, right? Which is partial L over partial SB times, sorry, partial AI. Partial L over partial AI, right? And partial SB. Okay, what's partial L over partial AI? 2 and 0.5 gets canceled, so minus yi minus AI, correct? And AI over SB depends on the activation function. Okay, let's pretend it's sigmoid, then what will it be? Remember, the derivative of sigmoid was f of x times 1 minus f of x. F of x is the output. So what is the output? AI. So this will be AI multiplied by, right? So anyway, that is the delta. Good. So now let's go, delta Bn. To compute delta Bn, how would we go further backwards? From here, where will I go to? Partial SB over partial SI hat. Then, so let's take a look at partial SB over partial SI hat. To focus on this equation. What's the answer? Gamma. Okay. So this is easy, right? Then further go back from here to here, because that is what delta Bn is. Okay. what is the equation for SI hat? SI minus mu B over sigma square B, right? So what will be partial SI hat over partial SI? See, if I separate it out, right, you'll say, oh, it's SI divided by sigma square B plus minus mu B over, so meaning, so what was it called? SI hat. SI hat. Okay, so SI hat equal to SI minus mu B over sigma square B plus epsilon, right? So my question is, what is partial SI hat over partial SI? Okay, so what I was saying is you may say, oh, let me write it like this, SI divided by sigma square B plus epsilon minus mu B over sigma square B plus epsilon, right? Now if I do the partial with respect to SI, what will happen to this term? You might say, oh, that will go zero. There's no SI in it, okay? But that's not entirely true. And the reason is like this. How do we compute mu B? Mu B is 1 over n's SI, right? It already has SI in it, so you cannot say, oh, so that is the complication over here. Same way for sigma B squared, that has SI in it. So for those of you with a little better calculus background, nothing complicated over here. What I'm trying to say is partial SI hat over partial SI is a little bit complicated, okay? Up to this point is no problem. This complication, because all three components over here, and the reason again complicated is because mu B is a function of SI, you can see. Sigma square B is a function of SI with a square term in it. So that's what makes the computation of the partial with respect to SI a little bit complicated. So I broke it into 3 parts over here. And then I do each 3 paths over here because there's 3 ways to go from SI to SI hat. One is, just this SI divided by. So anyway, if you go through slight more, steps over here, then I simplify those. The end result is, so I leave it as an exercise. Like I said, some of you feel pretty comfortable with calculus, so you'll be able to do it yourself. If you don't worry about it. I just wanted to show you at least the overall idea, which is that if we can figure out delta Bn, okay, then partial L over partial W1 or partial L over partial B is very easy because that will be related to this WBN, whichever input connects to the sum unit, that will be the answer, okay? The calculation of delta Bn is the tricky part, and that is because of this term over here. Okay, so anyway, end result is, if you go through some simplification, the final result is it becomes delta gamma over n sigma square B plus epsilon n minus 1 SI hat square, okay? And this is what we will program in assignment number 5, okay? And again, my recommendation is if you did take calculus before, please go through, see if I didn't make any mistake over here, okay? and see if this final result that I showed you each step is proper, right? So let's try to understand the final result. What is capital N? This is batch size. If batch size is 16, it will be 16, okay? Let's go to gamma. Gamma in the beginning, you can initialize it randomly or initialize it 0. It doesn't matter. And let's go to SI hat square. Okay, so what is SI hat square? Okay, SI hat is SI minus mu B over sigma B square, right? So that is basically the mean of the batch divided by the standard deviation of the batch for each of this sum that we are producing inside the neuron. So that could be easily computed. Okay, and okay, going back to the, so anyway, this during the forward pass, we are already computing SI hat square. So once we go backwards to compute the delta, that is simply the square of the forward pass. Just like, in a sigmoid, if we know the output, the derivative going backwards is output times 1 minus the output, right? Delta is whatever we already know inside the neuron. So going to the delta part, that is this regular delta that we already know how to compute, right? Which we already talked about how we will do this from here to here, here to here. So delta is already known. And lastly, this is the standard deviation of the batch and the N and so on, okay? So anyway, this is what we'll program. So going back to the assignment, hey, so the learning rate optimization, basically, which is implementation of the ADAM, we will implement the exact original equations, dropout. Dropout in Python as you program, I think I talked about it, but if not, let me quickly show you in Python. Because in dropout, what we want to do is randomly select some of the outputs of the neurons and zero them out, okay? So Python has this NumPy, in the NumPy, this binomial distribution, okay? If we say 1.8, and this is, so if you have 20 neurons, for example, right? Which means they will produce 20 outputs. But let's say 20% of them we wanted to zero out, okay? So this you will pick on based on the number of neurons. This is your dropout rate. So if you wanted to keep 80%, but drop out 20%, you'll pick 0.8. So what this will do is it will give you 20 numbers, okay? Randomly, 20% of them will be zeros. So what you will do is you will multiply this by the outputs that are coming out of the neuron. So you can see wherever the 1 is, it will, if the output was 0.3, it will keep it 0.3. If let's say the fifth output over here, suppose it was 0.19, but over here, the fifth output coming out of the binomial distribution is 0. So you can see as it goes to the next neuron, it will be zeroed out. So dropout is implemented by simple, this type of Python code, one line of code. So that is straightforward. coming back to batch normalization, the final equation that I showed you, you'll see I'm programming that in the code. Okay. And then you will test it on the MNIST data, see whether if you use Atom, if you don't use Atom, you will experiment with it. Hey, does it converge faster to whatever the desired goal is or not? So go through the code, go through, read the original paper on Atom to get an idea of it. Go through my derivation of batch normalization. If I made a mistake, let me know. But the main thing is that after you do assignment number 5, then our knowledge of the foundations of neural networks, in my opinion, is very solid, very complete. Okay, from a neural networks point of view, you know, like I said, the concepts are how do we create layers? What are the different activation functions? What are their derivatives? Okay, the delta rule that we talked about, which helps us, for example, if we know the delta at a certain point in a neuron, right? It doesn't matter, let's say one of the weights is WX, which is connecting to some output, let's call it Z as an example, right? So doesn't matter how many layers we are, what will be partial L over partial WX? It will be delta times Z, whatever the input that connects to that weight, right? What about the bias? Let's see if everybody remembers. What will be partial L over partial B? Same as delta, okay? So hopefully you guys are getting, okay, this is how neural networks learn, right? We talked about stochastic gradient descent algorithm, where we are applying this to the batch of data. When we compute partial L over partial data, we won't do it on one example. We'll do it on a batch and take the average of the batch and then compute the loss, derivative of the loss with respect to the weights, and then adjust the weights on the average, okay? Today we talked about, we had talked about also dropout and weight regularization, which are the techniques to prevent overfitting, as an example, so that model that performs well on unknown data, not just the training data, right? And to further be able to create more deep networks and have a stable training, we use batch normalization, where we add some additional computation inside each neuron, which you guys saw. One part was subtracting the mean, dividing by the standard. The other part was further doing the scaling and the shifting of the, so that introduced tiny bits more complication. Okay. One important point I want to make is, let me go back before I stop for today. Let me go back over here. Okay. So from batch normalization point of view, right? As you guys saw, we added this minus mu divided by standard deviation, this SI hat, right? We added this scaling and shifting layer as well, okay, which requires us to compute delta BN as an example. As you can see, when we apply this, right, we are applying it on the mean of the data and the standard deviation of the data. So the question is, during testing, once the network is trained, which mu and standard deviation should we use? Because when we do the actual testing, we don't pass it a batch of data. We only pass it one data item, right? in the answer as you do, or let me not give you the answer, at least have you go through the code. If you can add this answer in your code, like how is the batch normalization being handled during testing? So that is one of the things I like you to think about it. Because in testing, there is no batch. Okay. So you'll investigate. Anyway, try to do a really good job on this assignment, as well as assignment number 4. Sorry, not this one. Where did it go? Okay. Then your fundamental knowledge is complete, almost complete. We can never say we, we know everything. Okay. Then we'll start to take a look at convolutional neural networks, and I will introduce PyTorch library as well. So that now you know how internally these things work. So there's no need for us to do everything from scratch. So next lecture onwards, we'll make it more productive. Okay, keep up the good work.